John Dennis, and I'm Master Black Belt with the International Lean Six Sigma Institute based in Cambridge, England. And I would like to present a video which is going to explain a way to teach two of the new tools in SigmaXL version 9.1, which are Advanced Multiple Regression Analysis and the Multiple Response Optimization tools. And these two tools are extremely useful and new. So if I just close that window there, in the statistical tools, we have the two items: Advanced Multiple Regression, which is fit multiple regression model, and Multiple Response Optimization in sets of colors, and some of our training partners have these delivered to you as part of the training class. And I've just got the three colors here, and as you can see, I've already taken some of the Play-Doh out of the, prepared something before, taken it out of the tubs. We've rolled it into a ball there, and we have a digital scale here, which if I turn it on here, I don't think you can read in the video, but this ball we have as 10 grams, and the small ball is 10 grams, the large ball is 20 grams. And we have the same for the blue: small blue 10 grams, large blue 20 grams. Your students will be doing this in the classroom. They will have to weigh out, and it doesn't have to be exactly spot on 10 grams. You can give them some tolerance limits, so plus or minus 0.1 grams, so 10.1 to 9.9 grams will still give the same demonstration. So we have the three colors, the six balls they're made up. We have a digital scale, and later on we'll also be using a vernier caliper, and these can also be purchased online. These are reasonably inexpensive for training partners to purchase, under $10, around about $10 per vernier caliper. This plastic type, you would not probably, well, you would not use this in industry. It's not robust or precise enough for industry, but it works for this. And you would be building up data tables like this. You might be able to ask your IT department for this data, or you might have to run an experiment to collect this data. So how does regression analysis work? Well, regression analysis in SigmaXL, if I just show you the old regression analysis first, you highlight the data that you have, you go to statistical tools, regression, multiple regression. Next, it wants to know what is the response variable. The response variable here is total weight. The continuous predictors, the continuous X's, are the red, the blue, and the white. We don't have any categorical predictors in this particular experiment, in this particular regression. And you can do a regular regression or a standardized regression using normal distribution, or you can use a standardized regression using t-distribution. We will discuss the difference between these. Regular is sometimes just called non-standardized, and it is okay to use if your input variables all have the same units. You are consistent with the units you're using, in this case grams, grams, grams. You could use the regular regression. If your input variables have different units or different scales. So for example, if you're measuring one input in grams, but the other input in kilograms, then you want to standardize those inputs so that the system is not, for example, thinking that the grams, because the 1,000 grams is a much bigger number than 1 kilogram, is having a much bigger effect, or in fact it would act like it has a smaller effect, because you need 1,000 of the grams to make up the same effect as 1 kilogram. So if you've got different units or different types of inputs, such as one is temperature, one is pressure, then the other one is speed, then use the standardized. Let's just have a look at this with the regular, because we are using the same units. If I click OK, we're going to be getting the multiple regression equation, which says total weight. Now that, which is 5.7 e to the minus 14, that is the scientific way of expressing a decimal. It's scientific notation. And when you see e to the minus 14, this is, and e stands for exponential. It means 5.7 times 10 to the minus 14, which is the same as 0 point and then 13 zeros with 5.7. So that is an extremely, extremely small number, and it's equivalent to 0. So you have to interpret that as being 0. So the constant is 0. Then we have 1 times x3, 1 times x2, and 1 times x1. That is what we would expect, knowing that total weight is x1 plus x2 plus x3. The coefficients each are 1. The coefficients are 1 here. Coefficients are 1, and the constant is 0. So this is what our regression equation is telling us. Now, in this old regression analysis, we could predict what an output would be based on this regression equation. So we could put in, for example, 7, 6, and 10, and based upon the equation, it's going to tell you the predicted response is 23. So knowing the inputs, we can tell the output. However, this would not tell you what the inputs should be, or the best settings for the inputs, if you want a particular output. So I could not put in the number 23 and expect it to tell me the input settings. The good thing about the new advanced multiple regression is it can optimize your output to whatever target you're trying to hit, or it can maximize it or minimize it. So let's have a look at that tool. So SigmaXL, we're going to go back to sheet 1, and these numbers that we've just we found by collecting data from the process, or we've asked our IT department to give us these numbers. And if we highlight the data again, and we go to SigmaXL Statistical Tools, Advanced Multiple Regression, you'll see here it says Fit Multiple Regression Model. Well, the difference between saying Fit Multiple Regression Model and just multiple regression isn't too significant. I wouldn't worry about that. The point is, this tool will do optimization. So I'm going to click that, and next. The interface is slightly different to the interface for the standard multiple regression, the old multiple regression tool. You still have to choose the response variable, and you have to choose the predictors. Instead of it asking whether you want regular or standardized, here it's a checkbox. So you either click it if you want standardized, or you uncheck it if you want what used to be called regular. So to have regular, and I said regular is okay if you've got the same units, you'd uncheck that. And let's have a look at the main effects plots and interaction plots as well. And we're going to click next. And this is a slightly different element as well in the new multiple regression tool. You get a second window here where you choose whether you want to just include the main effects or you want to be examining interaction effects as well. So let me just put in all the effects. So you have 3 inputs, therefore you can possibly have 3-way interactions. Let's put all of the possible combinations there and see what happens. So we're going to select all and we're going to click OK. Okay, so we have total weight. The constant again is a very, very small number. It's 3.05 e to the minus 15 in scientific notation. So that is 0.0 with 14 zeros and then 305. So it's essentially 0. Then you have 1 times the red plus 1 times the blue, 1 times the white. And what are the coefficients for the interactions? 0. And this again is essentially 0. 2.7 e to the minus 16 is essentially 0. So we have no interaction effects there. So the main part of our equation here is here. If I just make it bigger, that is the main part of the equation. The interaction effects have no effect. So if I wanted to simplify that, what I would do is go SigmaXL. I can recall dialog and run this again, but I'm only going to put in the main effects now because I've shown that there's no interaction effects. So let's have a look. Remove all. Now we'll just do main effects and select all main effects. And because we've determined that the constant is 0, I'm going to remove the constant so that it doesn't confuse you with the scientific notation of 0, which is, as I say, just a very small number. So I won't include the constant and click OK. Okay, now we have a much simpler regression equation there. Can you see that? Okay. We have total weight equals 1 times x3 plus 1 times x2 plus 1 times x1. It doesn't matter what order they are in. It could have been x1, then x2, and then x3. It's just because of the order you select them in that last tool. So we've got the coefficients as 1, and this is indicating that each input, the white, the red, and the blue weights all have an equal main effect on the output. So any variation in red has the same effect on the output as a variation in blue or a variation in white, and that's what you'd expect. 1 gram equals 1 gram equals 1 gram. A change in 1 gram has the same effect on the output weight, irrespective of color, independent of color. You will know from Greenbelt, for example, these p-values mean that this is a significant regression, so we can have confidence in these numbers. Now, what I was saying about the optimization tool here. So we go over to this side of the page, And we have this button called Optimize. Can you see that button called Optimize? And you can choose a target for your output. Okay. So if I wanted to say what would be the best input settings to get a target of 19, I can click on 19, then click Optimize. And it says, do you want to paste the new predictor values? And it'll put the predictor values in here. So it's basically come up with a combination which equals 19. It could have come up with many other combinations, but it chose one combination that will equal 19. And that is, it's irrespective of which factor. It knows that the factors all have equal weight. And so it can, it will choose them in this way. So that is the predictor. Okay. Now, once you have predicted, you've run this tool on one output, like weight, we can run it again on a. Let's look again at the scenario that we're using in terms of the inputs, the process, and the outputs. So let's look at that now. This is the scenario. We have the three inputs, X3, X2, X1. X1 is the weight of the blue, X2 the weight of the white, and X3 the weight of the red. In a designed experiment, they're often referred to as A, B, and C, the three factors. But we generally call them X1, X2, X3. The transformation is where we're combining the inputs, and every process is different. In this case, all we're doing is combining them together, and we're going to weigh the output there, and we're also going to measure the diameter of the output. So we've just ran a multiple regression, an advanced multiple regression with the optimizer for Y1, which is the weight in grams. Next, we're going to run the advanced multiple regression for Y2, which is the diameter in millimeters. So I hope everybody's following us there. So let's see what we're going to do for the Y2 now. So Y2, which is, we're going to go back to our first data input sheet here. And what we're going to do is create another. We're going to create Y2, which is diameter in millimeters. So let's just format that the same way as we have the other one. Right, Y2 diameter in millimeters. Just format that. Okay. So in this particular case, you would not be able to just guess or predict without doing the experiment what the diameter is. So in this case, we would actually have to get 5 grams of the red, 5 grams of the blue, and 5 grams of the white. So this is what I'd like people in your class to do. Actually, to weigh out 5 grams, take the scale, turn it on, and weigh out the 5 grams of each color. So that's what I'm going to do now. there's 5 of the red, and I'd like people to do this in the class. There's 5 of the white, and here is the blue. Five of the blue. Yep. Okay. So I will stop share there actually and show you approximately, we've been weighing them out. So here is the 5 of white, there's the 5 of the red, and there's the 5. And what is the output? So the output is combining these together and rolling them into a sphere, into a ball. Okay. This is the process. Look, we've got the ball there. Okay. It's quite cool. All right. There is the ball. Now, we're going to measure the diameter. So we take the vernier caliper, which I said these can be purchased relatively cheaply, $10 or less, and it says 0 in millimeters, and these are not really good for industrial manufacturing purposes, but you can see there we have a pro. Okay, so I'm going to show you the difference between the regular regression analysis tool, which SigmaXL has had for a number of years, and the new Advanced Multiple Regression analysis tool, which has the optimizer function. So the old regression analysis and multiple regression analysis did not have optimizer, whereas the new one, which is called the Advanced Multiple Regression, has an optimizer in which, after running regression, you can then decide to set a target for your output, or you can set it as maximize the output or minimize the output, and the optimizer will find the best settings for the inputs. So to put that in another language, the optimizer will optimize the response from the regression. The response is the output by telling you the best settings for the predictors or the factors, which are the inputs. So let's take a quick look now at the SigmaXL menus that you'll be using. So I've just set up a sheet here in which we've got 3 inputs, X1, X2, and X3. And the inputs are going to be the weight of Play-doh that we use as input. So we have the red, the white, and the blue Play-doh. And in the class, you'll either have this in the classroom, or hopefully if you're doing this on Zoom, the trainer has got some Play-doh so that you can try this yourself, has sent you Play-doh. So this is the scenario. So let's take a look at the Y2, which is the response, Y2 output, which is the diameter measured in millimeters. So let's take a look at that and how we're going to deal with that in SigmaXL 9.1 multiple regression analysis. So let's take a look. Share screen. Share. So what we're going to do is we're adding this extra column here called Y2 diameter, and that's in millimeters. And what we're doing is seeing what is the diameter of the output when the weight is 555. So I'm just going to change camera now so that we can see me. Okay, hi. So 5, 5, 5. So that's saying 5 white, 5 blue, 5 red. So if we take 5 white, right, and we weigh 5 white, we try to find 5 white. Okay, we're taking the scale, we're weighing 5 white, right? I could actually stop share and show this. Well, it's not as easy as I thought. I have to move that back a bit, right? Okay, there you go. So 5 white, take a bit off, right? That's 4.84. Right. Okay. 5. Right. That's 5 white. Okay. That's 5 white. So now we just need 5 red. This is what you should be doing in the class as trainers with your class to get them to do this, and they will learn a lot from it. That's 3.6. They will learn a lot from this. 4.7. Okay, that's 5 exactly. Okay, so you get the 5. That's 5. That's 5 red and 5 whites. That's 10. And then we just need 5 blue. So I'm going to take this 5 blue. .2, bit more. Come on, let's go. I hope you're going to give me some likes for this, because this is not easy. Okay. All right, that's 5. Okay, that's 5. Great. So we have the 5 blue. Okay, we have the 5 blue, the 5 white, and the 5 red. Now that's the input. Okay, so we take the input and we say, what is that weight? Okay, what is that diameter rather? So we roll it together. This is what your class are going to do, right? The output, what is the diameter? Now this is something they could not guess. They could not just anticipate. So let's do this. Let's do 0. Okay. So what do we got here? Oops. 0. What's that? 33.2. 33.2 millimeters. Okay. Do you agree with that? Oops. Let's do that again. Let me roll that again. Okay. Oh. Okay. Great. What is that? 27.0. 20. I'm going to take that one. 27.0. Okay. So what do we do? 27.0. Share screen. I put in. Let's just delete these numbers here. 555 is 27 millimeters, right? So you would do this with each of these. So 10, 2, 2, 3, 1, 1, 4, 5, 6. So we would find the diameters. So let me just quickly find approximate diameters of the other ones, right? Okay. I mean, 14 versus 15 with the measurement system analysis error is going to not be that much different, I don't think. Let's have a look. 0. Yeah, so that's 26.3, 26.3. Okay, 26.3. And the next one is 5. So 5 is 3 plus 1 plus 1. Okay, here we go. 5 is 18.1. A lot of measurement system error in here. 15, let's put in 27 again. And let's put 18.2 in here for the 16 and 88. I actually happen to have an 88 approximately made here. So 88. Oh, bit more needed. $80, that's 80. Okay, so we need a bit more. All right, 88, 86, 86, 88, 88. Okay, so 88 we have here. This is what 88 looks like. Okay. Back to 0, open it up. And the diameter is, what's that? 47.2. So you put in 47.2. Okay, so now what have we got? We've now got the response in diameter for the 3 inputs, X1, X2, X3. And we're now going to run a regression analysis on diameter. So we highlight the data. We go to SigmaXL, statistical tools, advanced multiple regression, fit multiple regression model. Next. The output, the response is diameter this time. And the inputs are, no, not total weight. Let's delete that. Let's remove that. Let's go the white weight, the blue weight, and the red weight. Okay. And we're not going to standardize it because we know the units are the same and it's on the same scale. So we don't need to standardize it. We say next, actually we'll do main effect plots and interaction plots. That's not important. We're really looking at the now. Let's do the main effects again and not include the constant, because again, we expect that if there was 0 weight, then there'd be 0 diameter. Okay, so if I click OK, model, sorry, select all, right. Okay, so what have we got here? We got a more interesting equation. We have a diameter based on 2 times white weight, minus 3 times blue weight, and 6 times red weight. So that is surprising, since you would think each would have the same weight, same effect. And actually, we've got one that is not significant either. So what this is showing is that the variation in the diameters was such that it was not a perfect correlation. So the number of points we have were not enough to show significance. All right. So we'd have to have more points, more data points, in order to show significance. But that is the regression equation that was produced. Okay. we would probably want to repeat this. We'd probably want to go back to our sheet. Because it's not significant, there's not enough points for significance. We'd want to collect more points in order to get a good regression here. Let's move forward, because this is the 3rd time I've made this video, and I'm certain I want to finish this time. So let's move forward and say, let's assume that this regression was good. Okay. So here is the we're getting the diameter. Yeah, there's the diameter. There's the diameter regression equation. So we've got a weight regression equation and a diameter regression equation. And now we're going to use the wonderful multiple response optimization tool. So what you do now is go to SigmaXL, statistical tools, and advanced multiple regression, multiple regression optimization. And what it's going to show up are any advanced multiple regressions that you've done in this workbook. So it's going to bring up all the worksheets that have been produced. And what we have are 2 that we did for the total weight and 1 for the diameter. So let's take the total weight as a response and the diameter as a response. And what this tool does is allows you to either set a target for the response, or you can go maximize, minimize, or maximize. So let's say we wanted to maximize the weight but minimize the diameter. That's what you would choose. And then you don't need a target in there. You don't need lower or upper. You can just have maximize and minimize. What this weight and importance is a way to prioritize when you do the optimization, one output over another output, one response over another response. So let's say we want to optimize based on a weight more important than diameter. Then we'd put a 2 in the diameter rather than a 1. And then we just click OK, and it will optimize for weight based on maximum weight. Okay. So here we go. It's saying that in order to get maximum weight and minimum diameter, we want to have 19 on the white, 13 on the blue, and 2 on the red, which will give a predicted response of 35. The diameter will be 19. Okay, so I hope you can see that in the predicted response. So it predicts the best input settings to give you the maximum output or the minimum output, or you can set a target also. So the next section, what we're going to do, instead of choosing these input variables randomly, we're going to do a designed experiment. So follow along with how to do a designed experiment. Thank you. Has the DOE, design of experiments here. We go to 2-level factorial screening and the screening designs. And so we have 3 different colors and 3 different input variables here. So I'm going to change that to 3. I'm going to make it a full factorial experiment, and I'm going to actually replicate this 3 times so we can get better statistical significance. The replication improves statistical significance, more likely to get a low p-value if there is significance. So let me just put in here, I'm just going to see what I called them in the first part. I think I had A. I have to go back and see what I called them. So we had A as white, yeah, B as blue, and C as red. So let's go back to here. Design of experiments. Okay, 3, again, 3 full factorial, 3 replicates, and then we're going to put the word, white in here. We're going to put the word blue in here, and we're going to put the word red in here. And we've got our low and high levels for each factor, each input factor. So what did we say our low level was? Well, our low level, in this case, we're measuring grams. Our low level is the weight of the small ball. So I'm going to put in 10 for each of the low levels here. And what's the high level? The high level is the large, so that is 20 grams. Okay. What is the response? Well, what are we going to do with these input variables? Actually, what we're going to do is combine the 2 balls into 1 ball. So that is the process. The process is taking two inputs and combining them. Not 2 inputs, but we're taking 3 inputs. We're taking 3 inputs, and we're combining them into 1 output. 3 inputs, 3 factors into 1 output. So we're going to combine these, and the output is going to be the weight of the combination. Now, this is a good practical experiment to do with students because the outcome is obvious. It's common sense what the outcome is. If we have each ball weighing 10 grams and we combine them, we mush them together, right? And then we weigh them, what would we expect the output to be? What would we expect the output to be? Hopefully, all of you can see that that would be 10 plus 10 plus 10 of 30 grams. That's the output. Now, what about if we had a small white input with a large red input, right? Well, combine those together, we have 10 grams plus 20 grams, which is 30 grams. Okay. We have 30 grams there. Okay. But we're actually doing 3 of those. So that last example should have been one large with 1 small and perhaps another large. What would that be? That would be 10 plus 10 plus, 20 plus 10 plus 20, which is 50. That's 50. Okay, that's 50. So what is the response? The response we're going to call total weight. Total weight. That is the combination of the input variables. Okay. So that is the design of the experiment. When I click OK, it produces all the combinations of the input variables, right? Which then is the experiment which we have to do and find out what the output is. So if I click OK, okay, it's produced a worksheet here for running that experiment. And for those of you who have done the basic fundamentals course in Greenbelt on DOE, you would know that if we have 3 factors with 2 levels, then that is a 2 to the 3 design, which would have a minimum of 8 experimental runs. We have done this with 3 replicates. So 3 times 8 is 24. Hence the 24 experimental runs. And it's telling you for each experimental run what combination to do. So it's saying the first experiment is combine a 10 from white, which is this one, with a 20 from blue, which is that one, and a 20 from red. Okay, right? So what we would be doing is the process is combining those into one output, and the output is the total weight. Okay, so if I just stop share there and go to the other camera, okay, what your class should be doing is visualizing and understanding what's going on here. The output is a combination of the 3 inputs: large red, large blue, small white. Or you could say a low level for white, a high level for blue, a high level for red. And you could ask them to weigh this, right? If we weren't sure what that should be, we would weigh that, right? Put it on there, right? And we get the 50 grams. The 50 grams, I'd really expect 20 plus 20 plus 10 is 50 grams. So the output is 50. So what do we do in the experiment then? Well, we would go to our SigmaXL and we would put in a total weight there. We type in 50. Okay. Now if you were doing a real experiment, you'd have to take each of these inputs and do the process and see what the output is. In this case, the next one is, we'll do it one more time. Large white, a high for the white, a low for the blue, and a low for the red, right? So again, we're going to then find out what is the output weight, what's the total weight. So we would go to our scales. We're just going to do this one more time. So for anybody that's still not clear, we would go to our scales. Weigh that. And we get 40 grams. Surprise, surprise. We get 40 grams. 20 plus 10 plus 10. Okay. So what do we do now in Excel? We go to SigmaXL, and it was 40. We type in 40 there. your students will quickly catch on what's going on. They don't have to weigh them because they know logically what it should be. So 10 plus 20 plus 10 here, that is another 40. 20 plus 10 plus 20 is another 50. So we have 50s and 40s, but as you go down, you're going to find one of them, which is 10, 10, 10. So this one is only 30, not one of them. You'll find three like that because it's been replicated 3 times. There's a 10 plus 10 plus 10, which is 30. We also have some 20s plus 20 plus 20, which is 60. So if you do this and complete this table sheet, you would go to design of experiments, 2-level factorial, / screening, analyze, screening design. The response is total weight, and we can put in all the model terms here, all the model terms, which means we have the main effects plus the 2-way interaction effects plus the 3-way interaction effect. If you're watching this as a student and you're not getting what we mean by interaction effects, this is part of the green belt course. So this video is really for black belt, and you need to do green belt basic DOE before you get into this video. And a trainer will help you with that. So all you do then is click OK. And what do we get? Okay. Well, what the DOE does is gives a standardized equation here, or it's sometimes called a coded equation, a coded or standardized equation, which says that the total weight is 45 grams plus 5 times the weight of A plus 5 times the weight of B plus 5 times the weight of C. And then there are no interaction effects. Well, we might have thought by common sense that there's no interaction effects. That is, the weight of whatever weight A is, or white, does not affect the weight of B. The weight of B does not affect the weight of C, and there's no interaction between any of the weights, so they don't affect each other, and that's why there's no interaction effects. But you might be confused or surprised why the equation doesn't just say total weight equals A plus B plus C, and that is because this is a standardized equation where it takes the average of the weights, of the output weights. Now, the average of the output weights, as you know, the smallest weight it could be is 30, which is 10 plus 10 plus 10. The largest weight is 60, 20 plus 20 plus 20. So the average weight is between there. The mean average is 45. And it takes that 45 as if it was the 0 position. So that's your basic default position, 45, the mean average. So our starting position is 45. That is, if we don't add any of A, B, or C, we get that 45. That's why the 0, when all the x's equal 0, y equals 45. And then where does the 5 come from? Well, the 5 is actually the standard deviation of the difference between the smallest level and the highest level, the lowest level and the highest level. This is how a coded equation is constructed, and it can be very useful when you have more complicated systems. In this particular case, I don't think this equation is as useful as the uncoded or the unstandardized equation. But luckily for us, in the DOE tool, we do have a predictor. It's using that equation, and you can actually put in the actual values, or you can put in the coded values. So the actual values, sorry, you can't put in the coded, you have to put in the actual. So let's say we didn't know if we had, say, 50 grams of white, 50 grams of white and 5 grams of blue and 1 gram of red. We didn't know, we wouldn't know what the output was because the process is complicated. We might not know what that it's just adding them together. So this calculator will actually predict for you, it'll predict what the output should be. So it's actually got that correct. It's predicted it as 50 plus 5 plus 1 equals 56. But it used the prediction equation. Okay. Prediction equation. So what I created there was the 2 20s and 1 10. I'm going to combine them together. 2 20s and 1 10. You'd expect that to be larger, right? So we take the caliper, we're making a sphere out of it, and what do we get? 47. Okay, so 47 is the 20-20-20. Then we have a small, large. We've already done one of them, so that should be 40. Let's just recap. We have 3 input factors. We have white, blue, and red weights, which are input factors. They're continuous variables. We have an output factor, which is the total weight when we combine it, which is also a continuous variable. And we have the diameter of the total. And we might actually, for clarity, put total diameter here. Just for total diameter of the output, right? And we're going to use this, we're going to highlight the data now, highlight the data, and we're going to say SigmaXL, statistical tools, Advanced Multiple Regression, and Multiple Response Optimization. Okay. Before I do that, sorry, I need to run, before I can do the Multiple Response Optimization, I need to run the Advanced Multiple Regression just on the total diameter, because we haven't run the regression on that yet. Okay, so we could actually do it. You could actually do it by highlighting. Now we have to run statistical tools, advanced multiple regression, fit multiple regression model. But what we're going to do this time is our response variable is total diameter. Okay. And our continuous input predictors are the white, blue, and red weights. And again, we're going to unstandardize it, and we see what the equation is it produces. So we can, if you want to look at main effects again, and we'll run that. So we'll do this one. Now, this is a little more complicated because it's how does the input weight affect the output diameter? So it's not going to be simply an addition. Select all, main effects, and we will include the constant this time. Okay. So what do we have here? We have the total diameter is equal to a constant 17 plus, and it's got 0.5625 times the white weight, 0.256 times the blue weight, and 0.526 times the red weight. So that is what we would think that the The different colors don't affect it because don't have any different effect. They have the same effect. So our Pareto again is it shows equality among the main effects, right? All 24 points, right? So now we've run both regressions. We've run it for the weight, total weight, and the total diameter. Now what we're going to do is be able to run the advanced multiple regression, multiple response optimization. So what this tool does is looks at which regression models do you have that have already been run. And we've got this one, which is the total weight, which is the last total weight we did. So that's response 1. And the total diameter is response 2. Okay. The reason why there was 2 more in here is because earlier I'd been doing some practice on this and I had not deleted those from my sheets. But if you have a clean start and you start this from scratch, you should only have 2 regressions, a lower and upper tolerance on the target. But if we chose to maximize the weight, then you would just put in, you would just take this out. You wouldn't have a target. You would just delete that and delete that, delete the upper, because you just want maximum possible. And you have 3 choices always. You have maximum, minimum, and target. Let's use the target, and we said 60 grams. And let's say we wanted it to be somewhere between 55 and 65 as our tolerance limits. The diameter, what is the approximate diameter of this, is about 50. So let's put a target of 50 and tolerances of 45, 45 rather, and 55. So what we're asking the system to do now is recommend to us the correct weights of the A, the B, and the C, the white, the blue, and the red, in order to get a target of 60 for the weight and a target of 50 for the diameter. Okay. If you want to put one of these output variables as more important than the other, it will prioritize based on the importance level. So I could put that it's more important to hit the weight than the diameter, in which case I'd put importance of 1 for weight, importance of 2 for diameter. The weighting is a bit more complicated. We're not going to get into that weighting. Just leave the weighting as 1. The importance, though, is quite straightforward. You can put it as importance depending on how you want it to optimize. Okay, so now I'm going to click OK. Okay, so what it's saying is here that if you use an input on the white of 20, an input of the blue of around about 20, 19.9, an input of the red of around about 20, you will get a target weight very close to the 60. The predicted response is 58, and it gives you the lower confidence limit and the upper confidence limit for that. And then the total diameter, it's getting it pretty close. It's getting it to 50.8, and it's giving you again a lower confidence interval and an upper confidence interval. So it's between 50.1 and 51.6. So as a process engineer, as a Lean Six Sigma black belt, you have to try to understand what these numbers are telling you and how to use these tools to help you optimize your processes when you have known input values, but you're not sure what the output value is, or you're not sure on the relationship of input to the output. These are very powerful and useful tools, but you must get used to what they're telling you. So in the black belt, we want you to understand how to use the DOE tool, how to use the regression tool and the advanced multiple regression tool. Advanced multiple regression. Multiple regression, by the way, just means that you've got one output with more than one input, right? More than one factor. And that's what we have. We have 3 input factors. And then we also want you to know the multiple response optimization tool, where you can give it 2 different outputs and it will tell you what the best setting of the inputs are. So hopefully, you know, with your digital scales, your vernier caliper and your Play-doh, you can have your students practice these tools. And the good thing about using this particular setup is that it can be intuitive to the student what should happen, so they know when something is wrong. Whereas if you're doing this with a system that you're not sure what should happen, then you have to trust the software that it is giving you the right answer, and you could be making you could be using the software wrong, or you could have done a fat finger typo, and you'd have to trust what the software was telling you. That's the beauty. Okay. So with that, I'm pleased to have eventually made this video, because as you can see, it's not that easy a video to make. We might do some editing, but on the whole, I think we've got the point across about using some practical tools and techniques, practical materials that a student can then actually put real world values into SigmaXL and get real outputs that should match what the reality is, or what their common sense understanding is of the process. Okay, so thank you very much. I'll stop the video there and I'll share it with a few of you. Thank you. Bye-bye.